Today's lecture is going to be on 4.1, which is solving systems of linear equations by graphing. So first we need to talk about what a system of linear equations is. And that is just a group of two or more linear equations. So for today, we're just going to work with groups of two linear equations. So for example, this just means that these two equations go together. They're part of the same system. Here is a system of two linear equations. And the first thing I'm going to do is show you how to determine whether a point is a solution of a linear system of linear equations. So what I'm going to do is I'm going to take these 2 points and substitute them in for x and y in both equations. So I'll take that first equation and I'll substitute the 2 for x and the 5 for y. And then I get 2 times 5 is 10, so 2 minus 10 equals -8. So this is a true statement. So that ordered pair is a solution of at least this equation. So now we need to try the other equation. Again, I'm substituting 2 for x and 5 for y. I guess I could write which equation I'm using up here. So that's going to be 10 minus 5 equals 5. And again, it's a true statement. So the answer is yes. Now, if either or both of these was false, then it would not be a solution. So I'm going to try a different ordered pair. That's a 0. And try substituting those values into the equation. So first I'm substituting 0 for x and 4 for y. That's going to be 0 minus 8. So this one is true. That is a solution of this equation. But if I plug those values in the second solution, I get 5 times 0 minus 4 equals 0 minus 4. So I'm getting -4 equals 5, which is not true. So it is not a solution of the second equation. And if it's not a solution of one, then it can't be a solution of the system. So no. Now we're going to get into the topic that the lecture is titled for, which is solving these systems by graphing. But first we need to introduce some terminology. The first 2 terms we're going to talk about are independent equations and dependent equations. So independent equations have different graphs. Basically, they represent different lines. So like y equals 2x. It's going to go through the origin. Here's going to have a line like that. Now, y equals 1/2 x is a different line. So these equations are independent because they represent different lines with different graphs. Dependent equations basically are the same line and the same graph. And you'd think this would be obvious, but I can write the equation for the same line multiple different ways. Like this one, I could rewrite by dividing both sides by 2. So then I would have to put these equations into the same form to see whether or not I have the same line. The next set of terms are consistent and inconsistent. So this is referring to a system. So if a system of 2 or more equations has a solution, or if it has infinite solutions, it is consistent. So it has at least one solution. Inconsistent means that the system has no solution. Now, we need to talk about what that means for lines on a graph. For lines on a graph, that means that they intersect. I didn't draw these very well. They should have been intersecting at the origin. But if they have a point of intersection, then they have one solution. 2 lines that don't intersect do not have a solution. And the only way for that to happen is if your lines are parallel. Because any other 2 lines will at some point run into each other. And then we also have this case where we have infinite solutions. And that is when we have a dependent system and both of the equations have the same line. Because no matter what number you plug in, if the 2 equations are the same, it's always going to work. So we're going to get into some real examples of those 3 cases right now. And for all of these, I'm going to, after we solve them, determine whether they're consistent and then whether or not they're independent. So the first system I have here, it's not going to be big enough. X plus y equals 2. And 3x minus y equals 2. So what I'm going to do is put both of those in slope-intercept form. So that's going to be y equals minus x plus 2. I'll divide by -1 on this one. So the 2 lines I'm working with are actually y equals -x plus 2 and y equals 3x minus 2. So I'm going to come over here and graph those. So my first line y equals -x plus 2. So I'll start with the 2, and then since it's -x, it's going to go down 1 and across 1. So go ahead and graph that one like this. This is y equals negative x plus 2. And then my second line is y equals 3x minus 2. So I'll start at minus 2. And then it has a slope of 3. So it's going to go up 3 and across 1. So that puts it crossing through right here. Whoa. Right there. And this point is going to be 1, 1. So that is the point of intersection. So this, if I ask to find the solution of the system, the answer would be 1, 1. So now this has one solution, and so that fits the requirements for it to be consistent. All it needs is at least one. So I'm going to say this is a consistent system. And it has two different lines. They're not the same, so it is also independent. Okay, so here's a system of two lines, and I've already put them in slope-intercept form. So all we have to do is graph them. The first one, y equals 2x plus 2, it's going to have an intercept at 2. And it's going to look like that. The second line has an intercept at negative 1, and it has the same slope, so it's still going up 2 and across 1. So these two lines are parallel. And as we went over before, two parallel lines never intersect. So they do not have a solution. There is no solution. So that means it's an inconsistent system. So we've covered the case where there's no solution, and we've covered the case where there's one solution. So here's a system of two equations. One's in slope-intercept form and one's in standard form. So I'm going to take the one that's in standard form and convert it into slope-intercept form by solving for y. And look what happens when I finish solving the equation. That should have been divided by 3. I get the exact same equation I had before. Since the equations are the same, I only have one line to graph, so I'll go ahead and graph the intercept. Take it down 1 and across 3. So any point on this line, let's say that's, I don't know what that point is. So any point on this line, here's 3, 1, 0, 2, is a solution of both equations, because both equations are the same. So what we would say in this case is the system has infinite solutions. So it is consistent because it fits the requirement of having at least one solution, and it is a dependent. The equations are dependent because they are the same. And that's all for section 4.1.